Hi, everyone. So today we're going to continue talking about evaluating limits using some of the algebraic simplification methods that we mentioned last time but didn't get to actually look at. So I want to start by just kind of reminding you the general idea of what we're doing in this section. And let me just write down that we're still in section 2.3. And this is all about evaluating limits using limit laws. So basically, general ideas, instead of relying on plugging in numbers or looking at the graph, we now have some kind of algebra tricks that help us to find limits. Okay, so the general principle behind what we're doing here is kind of reliant on two things. So two important facts that are kind of going on in the background when we're doing everything. So the first one is that if f of x is and I'm just going to write nice function. So what I mean by that is in the last video, I wrote out that whole long list of different types of functions. So basically any of the kinds of functions that you generally would have encountered, like trig functions, polynomials, rational functions, all those types of functions, we're not including piecewise functions in this description. So if f(x) is a nice function and f of x is defined at x is equal to a, then the limit as x approaches a of f of x is just f of a. So basically what that's saying is if you can plug in the number, you can just plug it in and that will tell you what your answer is, what the limit is. And then the other fact that we made use of is if you have two functions that are identical everywhere except for at one particular number, then what that means is that the limit as x approaches that number is the same as the limit as x approaches that number of the other function. So basically, we use these two facts that I wrote down in conjunction. What they mean is that by the second rule, if you're able to start with a function that is not defined at a particular value, and if you can make simplifications until you get a function that is equivalent, except that it's actually defined at that number, then you can go ahead and use the first rule and just plug in the number. So we covered a few different methods of algebraic simplification last time. So I want to write out, just remind you what these different kind of algebraic simplification methods are that we're generally using. So, so the general goal is to simplify the original function f of x to get a function g of x that, actually, that formatting is going to bug me. Let's go here. To get a function g of x that is defined at x equals a, and we're going to use the following methods. And so the method you're going to use, the algebraic method you're going to use, is going to depend on what type of function you're taking the limit of. So the first method that we saw last time was factoring and canceling. So I'm not going to actually do out these examples that I'm writing down. I just want to kind of have a reference example so you can see like what type of scenario would you use this for. So you'd use that if you had something like the limit as x approaches 2 of x squared minus 5x plus 6 over x minus 2. Because if you were to factor the numerator, you could cancel it out with the denominator. So using that method, when you see that, basically if you see that the numerator can be factored, and especially if you notice that if you factor the numerator, that something's going to cancel with the denominator. So second method is also used for polynomials, but it's used when you have polynomials that are maybe not fully multiplied out yet. And so an example of what that might look like is something like the limit as x approaches 0 of 5 plus x squared minus 25 over x. So basically the idea is if you were to multiply everything out, combine like terms in the numerator, then you'll be able to actually cancel out that x in the denominator. Okay. So third method, which this one is going to be new for today, is going to be doing something called multiplying by the conjugate. So I'm going to write down an example, and we'll come back and actually do this example fully in a few minutes after we talk about like what the conjugate is and all that. So an example of a place where you would use this method would be the limit as x approaches 0 of the square root of x squared plus 9 minus 3 all divided by x squared. So what we'll see is that multiplying by the conjugate is a method you're going to use when you have square roots involved, basically. It'll be a way to kind of get rid of the square roots and then also get stuff to kind of cancel out in a nice way. So the last method is going to be making a common denominator. And so making a common denominator is going to be any time where you have basically like extra fractions going on. So you might notice that all of these limits that we're looking at involve fractions in some way. But the example I'm about to write down is going to have kind of another fraction within that fraction. So, and we'll see later why it is that we're focusing on all these examples that involve fractions. There's a particular reason for it. So an example of this last one might be something like the limit as x approaches 1/2 of 1 over x minus 2 divided by x minus 1/2. So we'll do that example again a little bit later, but basically the idea would be making a common denominator in the numerator, making a common denominator in the denominator, and then doing some algebraic simplification. Okay, so let's look at that third method, multiplying by the conjugate. So there's a little bit of buildup we're going to do before we get to actually what that method looks like. Because in order to understand what's going on, there's a couple of other things that you have to know first. So the first thing is going to be just some kind of basic algebra that you might remember from your algebra classes, which is what's called a difference of squares. So an expression of the form a plus b times a minus b, and I'm going to leave some space to the right because we're going to multiply that out in a second, is called a difference of squares. And we'll see in a second why it's called that. So if you were to multiply together a plus b times a minus b, something kind of nice is going to happen. So if you multiply together the a and the a, you get a squared. Then you multiply together a and b, and you get ab. Then you multiply together again a and b, the other a and b, and you get minus ab. And then you get a minus b squared. And so what happens is that the middle terms cancel out. Because you have 1 plus and 1 minus, these two middle terms are going to go away. So you are just left with a squared minus b squared. And so that's why it's called a difference of squares, because it's difference means subtraction, and you're subtracting two things that are squared. So we're going to take advantage of this algebra to do something a little bit more complicated, but it's basically the exact same idea, which is that, again, if you have this plus and this minus, that's like really the important thing is that you have the exact same expression, but one of them has plus, one of them has minus. That's what's going to enable those middle terms to cancel out. So the conjugate of an expression of the form square root of a plus square root of b is going to be square root of a minus square root of b. So again, notice that similar to what we saw above, the only thing the only thing that's different between these two expressions is the plus and the minus. So why is why is the conjugate a thing? Basically because if you multiply an expression by its conjugate, the same thing will happen as we saw above with the difference of squares, and it will also get rid of the square roots. So if you multiply an expression by its conjugate, all of the square roots we're going to see cancel out. So if you were to take square root of a, actually, maybe let me write this below so I have enough space. Sorry, I'm just thinking about where I want to put it. I'll put it here. So if you have square root of a plus square root of b, and you multiply that with square root of a minus square root of b, so we don't have to multiply all of this out because we know what's going to happen because it's a difference of squares, right? If we look at what happened above, the middle terms, those are guaranteed to cancel out. So we don't need to write this out fully. Instead, we can just say, okay, we're going to have our first thing multiplied by our second thing. So we're going to have square root of a squared minus the second part multiplied with itself. So square root of b squared. And what happens when you square root and square it, the square root goes away, right? And so we're just left with a minus b. So why did I start by showing you the difference of squares? It's because I really, I want you to understand, first of all, why this works. And then also just moving forward, when you're multiplying something by its conjugate, I don't want you to go through all the steps of multiplying everything out. You can just kind of trust that it will work because of the plus and the minus, that things will cancel each other out. So let's do a couple of examples of this. So let's try to find the conjugate of, let's say, square root of x minus square root of 5. So how do you find the conjugate? You just flip that plus or that minus. So in this case, it's a minus, so we flip it to a plus. And then what would happen if we multiply them together? We would get, oops, that's not right, square root of x minus square root of 5 times square root of x plus square root of 5. So we know that those middle terms are going to cancel out. And then we're going to have square root of x squared, which is just x. And then we're going to have minus square root of 5 squared, which is just 5. So that's a fairly simple example. Let's look at one that's kind of more similar to the ones that are probably going to come up when you're doing limits. So when you're doing limits, frequently though, there will be slightly more complicated expressions under the square root. And it's really important you don't get confused about which sign you're flipping. So let's say instead that we are looking at the expression square root of x plus 4 plus 3. So when we're finding the conjugate, you're only flipping the sign that is between the two parts that are being, I guess, so maybe let me just point out something else that's different about this one. So this one doesn't have a square root on the second part. That's okay. So conjugates it's not always the case that both parts of it will have a square root, but we'll see that it's still a useful thing to do even if only one of them has a square root. But the important thing is that when you're figuring out, which sign are you flipping, you're always flipping this thing, the thing that's between the square roots or between the square root and the other thing. So, here we flipped this to a plus. So here, we're not going to do anything with the plus that's inside the square root. We're just going to flip that because that's the plus that separates the square root and the other number. So that's probably the most common place people make mistakes with this. So the conjugate will just be square root of x plus 4 minus 3. So we're just flipping this sign. And then if we were to multiply these together, so if we were to multiply these two things together, same kind of thing will happen as above. So square root of x plus 4 plus 3 times square root of x plus 4 minus 3. So the square roots are so we're going to do first two square roots times each other. Those will cancel out, so it'll just be x plus 4. And then we'll do minus 3 times 3, which is 9. And so this whole thing would simplify to x minus 5, which I guess is the same as the one above, but that was not really intentional. Cool. So that's conjugates, just flipping that plus or minus and seeing that it allows you to cancel out the square root. So let's do an actual example of this, of how we'll use this for finding limits. So let's say we wanted to evaluate the limit as, so it's the same one that I wrote down earlier. So it's the limit as x approaches 0 of square root of x squared plus 9 minus 3 over x squared. So first thing we want to do is find the conjugate of the numerator, because that's what we're going to take advantage of in this case, because that is what will help us get rid of that square root, and then we'll see that things kind of simplify nicely. So the conjugate of what we have here would be square root of x squared plus 9, so that part's staying the same, and then we flip it to being a plus 3. So we're going to multiply by the conjugate, but one thing that's really, really important to remember, and this is something that's like very common throughout all of math, is that when you're trying to take a function and simplify it or kind of rewrite it a different way, it would not make sense for us to just take this thing, this whole fraction here. It would not make sense for us just to take that and just multiply it by this, because that would be changing our function in a way that kind of goes beyond just simplifying it. So what we need to do instead is we have to multiply by that conjugate in the numerator and the denominator. So what we're going to do is we're going to multiply by the conjugate over the conjugate. And by the way, so there might be some examples where it's actually the denominator that has the square root. It's the same deal. Whichever part has the square root in it, find the conjugate of that, and then you're just multiplying by the conjugate over itself. So we're going to say the limit as x approaches 0 of square root of x squared plus 9 minus 3 over x squared. We're going to multiply that by square root of x squared plus 9 plus 3. And then we're going to do the same thing in the denominator. So it's going to temporarily look like we're actually making this kind of equally as complicated, but we'll see that things work out nicely. So let me go back over here. So what's happening with this limit? Well, the numerator, things are going to simplify the way that we saw in the other examples. So when you multiply this numerator by the other numerator, the square roots are going to cancel each other out. So we're going to be doing, this thing times this thing. And that will just give us x squared plus 9. And then we're going to do -3 times +3, and that's going to give us -9. So already we can see that something nice is going to happen there. So now in the denominator, this is really important. This is another place where people go wrong on these. You do not want to multiply things out. Leave everything kind of like unsimplified. So the way I'm going to write the denominator is I'm just going to say x squared times, and then I'm just going to rewrite that conjugate and just leave it there like that. Because so basically if you distribute, you're probably going to make it a lot harder for yourself to see what can be simplified. All right, so now we have the limit as x approaches 0. And so the numerator, we have a plus sign, we have a minus sign, so that just turns into x squared. And then in the denominator, because we did not distribute this, we can see that we have a common factor in the numerator and denominator. Both of them have an x squared. And so now we can actually go and cancel this x squared. And so what we're going to be left with is the limit as x approaches 0 of 1 over square root of x squared plus 9 plus 3. So maybe just there's something I probably should have mentioned earlier on, which is the goal is to get to the point where we can just plug in 0, right? So you always want to be, as you're doing this, kind of checking, can I plug in 0 yet? Can I plug in 0 yet? So initially we could not, right? We had an x squared in the denominator, we can't plug in 0. Even in the last step, so even if we go back to this step here, we still can't plug in 0, right? Because you still have this x squared in the denominator. But as soon as you cancel out that x squared, now we don't have just a plain old x squared in the denominator anymore. So the denominator will no longer be 0 when we plug in 0. So now we can actually just go ahead and plug in 0. So because we now have a function that is defined at 0, we can just plug in 0. So we'll get 1 over square root of 0 plus 9 plus 3. So maybe let me just write down what we're doing here. So now we can plug in 0. Okay, so now we're left with square root of 0 plus 9. So that's the same thing as the square root of 9. And square root of 9 is just 3. So we're left with 1 over 3 plus 3. And that is equal to 1 over 6. So that is our final answer for our limit. So they're all going to be kind of like this. So I'm not going to do another example of multiplying by the conjugate, just because I think you'll see that it really goes down very similarly. But I do want to show you what the graph of this looks like. So here is, and I was actually kind of surprised by what the graph of this looked like. I kind of expect to be a more interesting looking graph. You'll see that it's actually kind of boring. So here is our graph of our original function that we're taking the limit of. So it looks like a line. It's not. It kind of slopes downward a little, but it's almost like a horizontal line. But so for some reason, this shows up a little funnily here. So I don't know why the point shows up down there instead of on the graph. But the important thing is that this is not defined at 0, right? We can see that if you try to hover over 0, if I can actually get it to stay. Okay, well, you all saw it for a second, right? It's definitely undefined at 0. So if we look at what we got after multiplying by the conjugate and simplifying, we got this graph, and actually I have to switch the order. So yeah, so here is our red graph and our original graph, and here's our new graph, and then this one is defined at 0. At 0.0167, that is 1/6. So we basically just plugged in 0 into this function, and we see that the y value agrees with what we got. Okay, so let's do the other method. So the other method we haven't talked about yet is making a common denominator. So this is method 4. Okay, so once again, same example that I wrote out earlier. So let me just write that down. So that was the limit as x approaches 1/2 of 1 over x minus 2 divided by x minus 1/2. So basically we want to make a common denominator in the numerator and also make a common denominator in the denominator. So because if we look at focusing on the numerator first, we have 1 over x, and we just have 2. 2 doesn't have any denominator to it besides 1. So that means that our common denominator is going to be x. So to get that common denominator of x, what we're going to do is we're going to multiply 2 by x over x, and that will give us our common denominator. And then in the denominator, well, here we have x and we have 1/2, and so that tells us that we want to make a denominator of 2. So in this case, we're going to multiply x by 2 over 2. So it's not like we're going to get the same denominator in both the numerator and the denominator, but in each of them we'll now have we'll be able to kind of write everything as one fraction. So we won't have like so many different fractions going on. Okay, so our new numerator is going to be 1 over x minus 2x over x. And then here we're going to have 2x over 2 minus 1/2. So we made a common denominator so that we could actually combine what's going on here. So let's do that. So in the numerator, we have now 1 minus 2x divided by x. And then the denominator, we have 2x minus 1 over 2. Okay, so the next thing we're going to do is make use of a really, really important algebra fact. So in general, when you have a situation like this, you want to use the fact that if you have A over B over C over D, that's the same thing as A over B times D over C, right? So dividing by a fraction is the same as multiplying by the conjugate of that fraction. And so we're going to take this expression and rewrite it, instead of as a fraction divided by a fraction, we're going to rewrite it as a fraction times a fraction. So we're now going to have 1 minus 2x over x times, and then we take the denominator and flip it over, and so we have 2 over 2x minus 1. Okay, so before we go and multiply this together, we want to see if there's anything to simplify. So in general, when you're multiplying a fraction by a fraction, if there's a common factor in the numerator one and the denominator of the other, or vice versa, you can cancel before you multiply. And so in this case, you might notice that like these look pretty similar, right? We have 1 minus 2x, we have 2x minus 1. They're not exactly the same, but look similar. So we're going to use kind of a good fact to know, which is that in general, it's always true that if you have, let me write it this way, if you have b minus a, that's the same thing as negative a minus b, right? Because if you were to distribute in that negative sign, you get negative a plus b, which is the same thing as b minus a. And so what that means is that we can now rewrite this denominator of 2x minus 1, we can rewrite that as negative 1 minus 2x. And we'll see why that is useful in a second. So we can write this now. This one will stay 1 minus 2x, although you could switch this one. You could switch this being negative 2x minus 1. It doesn't make any difference at all. Let's do this denominator. Oops, I don't know why I said equals. Times 2 over, and then we're going to rewrite this as negative 1 minus 2x. Okay, so now what's going to happen is that now we can actually cancel out, because we have a common factor. We have 1 minus 2x here, we have 1 minus 2x here. And so what we're going to be left with is, in the numerator, we just have 2. And then in the denominator, we have x times negative 1 because of that negative sign. So we have negative x. And I guess once again, I forgot to talk about plugging stuff in. So maybe let's just backtrack for a second and say, initially we could not plug in the 1/2, right? Because we had x minus 1/2, that would give you 0 in the denominator. And then even if you looked at this next step, if you tried to plug in 1/2, you would still get 0 in the denominator, because you would have basically 2x over 2 is the same as just x. So you'd still get a 1/2 in the denominator. Really, things are still not going to be defined until actually this last stage. So like the stage where I circled it in magenta, where you have 2x minus 1, if you plugged in 1/2 at that stage, you would also get 0. So it's really not until we cancel out that, that denominator that we're going to be able to evaluate this. So now we can actually just go ahead and plug in 1/2. And so we have 2 over -1/2. And now we can actually use that same rule that we wrote up here in purple. So this rule. So dividing by -1/2 is the same thing as multiplying by -2/1. So this is the same thing as 2 times -2/1. And so that means that our final answer here is -4. So maybe let me just write down what we did here. So at this stage, we can actually just plug in 1/2 finally. Okay, so let's look at the graphs of these ones as well. So here is our original function. So this was before we did any simplification. So if I go to an x value of 1/2, you saw it, right? It said undefined for a second. Okay. I don't want to take your time with me just trying to do this, but you can see that it said undefined when we were at 1/2. And then if we look at the simplified version, so 2 over -x, that's going to be exactly the same graph, except for that this one actually is defined at 1/2. So if you try to go to 1/2, you actually get -4, which is what we found for our limit. So all we did was, again, simplify our original function to a nearly identical function that enabled us to plug in our number. Okay, so that is it for today. Maybe just give you kind of a heads up for what the rest of the week is going to be like. I think probably tomorrow's video and Wednesday's video are going to be a little bit on the shorter side. And then Thursdays and Fridays are probably going to be a little longer. I'm just trying to kind of split it up topically rather than splitting it up to be super consistent about the length of the video. So heads up on that. I'll try to get stuff uploaded in time so that, you know, if you do Tuesdays and Wednesdays quickly and you're looking for more, I'll try to get Thursdays up in time, you know, sometime on Wednesday. So just heads up on that. And yeah, I will see you all next time.